Hi guys, one more video here in Module 4 about augmented matrices. So we just showed in the last video how to use them to solve systems of equations. So by converting them to reduced row echelon form. But if you guys recall back in Module 3 when we were solving systems, it was possible to get systems that had one solution, no solutions, or infinitely many. We can have the same thing through the matrix process because it's still a system of equations. So remember, if it's an independent system, it's also called consistent. Okay, that's when I have one solution where I get an x, y, and z using the example for a 3-variable matrix or system. Inconsistent is when there is no solution, so we can use the empty set symbol or just write no solution. Okay, dependent is when we have infinitely many solutions. Okay, and we call that consistent as well. Okay, so for dependent systems, we always have to give one numeric example and the general algebraic answer. So I'll show you how to do that. So we're going to use our calculator here to help us out, but first I'm just going to show you some examples. So this is already in reduced row echelon form, so I have my identity matrix on the left with constants on the right. So this is independent and consistent because this looks just like our other ones where I have 1x equals 2, 1y equals -1, 1z equals 3. So my solution is an ordered triple, 2, -1, 3. Okay, so it's one unique solution. Okay, and these are planes, remember, x, y, and z. So the planes intersect at a single point. Okay, here is an example of a no solution or an inconsistent system. So remember what this means. This is saying 1x equals 2, 1y equals -1, and 0z, right, I have nothing in there for z, equals 3. So it's impossible for 0 to equal 3, right? No z equaling 3 is not possible. So when we get something like that, this is no solution. Okay, all three planes don't intersect is what that means. Okay, then let's see an example of the dependent consistent. So that's what this last one is. Okay, so here's what this looks like. So I notice in both the no solution and infinitely many solutions, I have zeros across the bottom. So that's kind of a red flag to look for. Then you just need to identify, is it no solution or infinitely many? Well, here, instead of 0 equals 3, I'm getting 0 equals 0. Okay, so that is true. 0 always equals 0. So this means I have infinitely many solutions. Now, if you guys recall the directions up above, let me scroll back up there. So for dependent systems, that's what we just found, always give one numeric example and the general algebraic answer. So here's how we do that. So I am going to actually kind of solve the remaining system. So here, I didn't completely get to the identity matrix. I have a 6 and a 4 left over, so I'm going to write out that system. So I have 1x plus 6z equals 2, okay? So another way to think about that is if I were solving for x, I would have x equals 2 minus 6z. If I do the same thing for the y equation, I have 1y plus 4z equals -1. Solve for y, I get y equals -1 minus 4z. So the generic, So I just rewrote these equations with the x and y. And so what I'm going to do, this is what we would call the general solution. Okay, is I have x and I'm writing it in terms of z. So x is this expression. So I have 2 minus 6z. Y is -1 minus 4z. And then z is itself. So it's all written in terms of z because it's called dependent because x and y depend on what z is. So to find a specific numeric example, all I have to do is plug in a value for z. Doesn't matter what I do. So this is a general specific, and I'm just gonna pick something. And I like to choose something easy like 0 or 1. So let's say let z equal 0. So I would plug in 0 for all these z's. So 2 minus 0 is 2, -1 minus 0 is -1, and we plugged in 0 for z. So this would be the general solution and the specific solution. All right, last part here, guys. Okay, so now we're going to look at kind of putting it all together. So finding the reduced row echelon form, finding our solutions, determining if it's none, infinitely many, or one solution, and if it's dependent, finding the general and specific. Okay, so I'm going to write the matrix out here first as an augmented matrix. So I have 4, -4, -3, 2, 4x, 0y, 3z, 0x, 4y, 6z. Okay, so then redo row echelon form. Okay, so let's see what we get here. So we got to enter these now into the calculator. So I'm going to matrix menu, edit. These are 3 by 4. I already got one of those in B, so I'm going to use that one. Going to the entries, I have 4, -4, -3, 2, 4, 0, 3, 3, 0, 4, 6, 3. Okay, redo row echelon form of that. All right, so we get this way. We have 1, 0.75, 0, 0, 1, 1.5, 0, 0, 0, 0, 1. Okay, so this is another kind of funky one. I didn't really get down to the identity matrix, but looking at that last row of zeros is really important. So another way to think about this, 1x plus 0.75z equals 0, possible. 1y plus 1.5z equals 0. 0z equals 1. So 0 not equal to 1. So this is no solutions. Okay, all right, try it for another one here. Okay, first write the matrix out. So 1, 1, -2, 0. 1x, 0y, -1z. 1x, -2y, 1z. Okay, redo row echelon form. So back into our edit menu. All right, so we got 1, 1, -2, 0, 1, 0, -1, -1, -2. Oh, I wrote a y in there. All right, let me get rid of that. Okay, redo row echelon form. Oh, shoot. Let's get out of there. All right, let's try that again. All right, so here's our redo row echelon form for this one. So we have 1, 0, -1, -1, 0, 1, -1, 1, and then all zeros on the bottom. So all zeros on the bottom, 0z equals 0 is infinitely many. Okay, but remember, if we have an infinitely many, which is a dependent and consistent system, we want the general solution and a specific one. Okay, so in order to do that, I'm going to rewrite those top two rows as equations. So I have 1x minus z equals -1. Solve for x. So x equals -1 plus z. Second one is 1y minus z equals 1. Add the z. Okay, so general, x is -1 plus z. Y is 1 plus z. Okay, so all in terms of z, I'm going to plug in 0 for a specific solution. So I would get -1, 1, and 0. Okay, all right. Remember, we want to have x's, y's, z's, and then a constant. So this one I could rewrite as 2x plus y equals 6. So that's important before we write our matrix. So I have just x's and y's. So it's 2 and 1 with a 6, -4, -2, -12. Okay, so this is a 2 by 3. So when I go into edit, I'm going to use my A there. It's already a 2 by 3. Enter these values. Okay, redo row echelon form. And this time we did matrix A. All right, so here I get, when I redo row echelon, we get 1.53 and zeros across the bottom. Okay, so this one would be another dependent consistent solution system with infinitely many. Okay, so general and specific. So this time I don't have z, I just have y. So my bottom equation is the one that is zeros across. So I want to solve in terms of that variable. So that's y. So we have an equation for x. So 1x plus 0.5y equals 3. So x is 3 minus 0.5y. So for my general, x in terms of y is 3 minus 0.5y. And then y, just write as it is. Plug in 0 for y to get a specific solution. And that would be a specific one that is a solution to the system. So remember, this is when planes intersect at a line and not a point, which is why there's infinitely many. This happens to be a point on that line of intersection. All right, I wanted to take a look at this one, you guys. If I wrote this one out, be careful. This one is not zeros across the bottom. It does have the identity matrix, but people can get thrown off when I get a 0 as a solution. But this is not a no solution example. So here, if I wrote this out, I have 1x equals 2, 1y equals 3, and 1z equals 0. That is possible. So this is a one solution example where 0 is the solution for z. So this is a one solution. It's an independent, consistent system, not a no solution system. Okay, last example for this video, we are going to write a system of equations and then a matrix and solve using redo row. Struggling saying that. Redo row. Oh my gosh. Echelon form. Row reduce echelon form. There we go. Okay, so let's read this and then determine what our variables are going to be so that we can write our system. So we have a shelter receives a shipment of items worth $1,040. Bags of cat food are valued at $5 each, flea collars at $6, catnip toys at $2. There are 4 times as many bags of food as collars. The number of collars and toys together equals 100. How many of each item are in the shipment? So this is my variables. So I'm going to let x be bags of cat food. That's one of the items. I'm going to let Y be the second item, which was flea collars. And I'm going to let Z be the last one. So Z was the catnip toys. Okay, so if I want to write a system that models this scenario, we have a total amount of $1,040 combined of a bunch of these items. So I can write one equation in terms of all the costs. So I had $5 per cat food bag, $6 for flea collars, and $2 for catnip toys. So that total had to be $1,040. So that is one of my equations in the system. When I have 3 unknowns, I want to make sure I have 3 equations. So the next sentence says there are 4 times as many bags of cat food as collars. So if I multiply the number of collars times 4, that would equal the number of food bags. So the number of food bags is X equals 4 times the number of collars, which is Y. The number of collars and toys together equals 100. So toys and collars are Y and Z. And total, there are 100 items. So there I have 3 equations and 3 unknowns. I'm going to rewrite this one as X minus 4Y equals 0, just so that I have it in that form for writing an augmented matrix. Okay, so here I have 5, 6, 2, 10,040. I have 1, negative 4, 0, 0, 0, 1, 1, 100. Okay, so there's my augmented matrix. We're going to enter it in the calculator here. So I have a 3x4 matrix. Entering those values here, we have 5, 6, 2, 10,040. 1, negative 4, 0, 0, 0, 1, 1, 100. Okay. Math. RREF. Matrix B. All right, so here is our reduced row echelon form. We have 1, 0, 0, 140, 0, 1, 0, 35, 0, 0, 1, 65. Okay, so this is a one solution example. 1x equals 140. Remember, x was the food bags of cat food, so we have 140 food bags. We have 1y equals 35. Y was the flea collars, so 35 collars. And 1z equals 65. 65 was the z was the catnip toys. So we have 65 of those. So that is how we can use a matrix to solve a system of equations, even if it's a word problem. Okay, so that's kind of combining all of our skills, you guys, involving matrices, as well as kind of what we learned in Module 3 over linear systems. That's it for this video. Thanks for watching.